Here we are. Hello, everybody. Здравствуйте. Bonjour. 你好, 大家. So, 你好. So, my name is Marat SAGYNDIKOV or SAGYNDIKOV. How to spell is comfortable for you. It's all options okay. So, I am an independent consultant from Kazakhstan. It's post-Soviet Union country and it's part of Commonwealth independent states. And I will talk about polymer flood, and I have extensive experience in polymer flooding, including all stage from screening, R&D, designing, projecting, feasibility studies, field implementation, field supervision, everything. And big part of this work has been supervised by my professor and PhD supervisor, Mr. Randy Sirait. I appreciate his guidance for me for all those years, and we did. So today I will present our achievements on this project. So I will start from introduction and go further for introducing polymer flood. It's the column-cast field first pilots, recent pilots, what we learned from them, how we did preparation of polymer solution, and find optimum injection system, how we found sweet spot selection based on numerical, modern numerical studies, analytical studies, combination, and finally, based on lessons learned, how we get to the concept or strategy of design full field deployment. Finally, feasibility studies and conclusion. So, column-cast field is one of the biggest brownfield in Kazakhstan. So Kazakhstan is a ninth place in area over the world. It has 2.73 square kilometers. It's 5 France. We have huge area, and we have 3 big oil fields. It calls Kashagan, offshore oil field carbonate reservoir, which is very similar with Middle East. TCO, also very huge carbonate oil field, and Karachaganak is a gas condensate field. So all of these fields is contributing to Kazakhstan production more than 50% of production, and they are green fields, and production is increasing year by year. So they limited only on gas production, and they have high H2S. That's why they need gas facilities to increase the production. Expensive. And other 40% of oil fields are referred to brown fields, 45%. So all these fields are declining, and some experts have a not bright future for us. So after 25 years, 20 years, we're expecting decline 4 times. And considering that our economy, 50% at least rely on export of this crude oil. So improving oil recovery, enhancing oil recovery is crucial for our being in Kazakhstan. That's why column-cast field was considered as the first best candidate over all these fields. So this field was discovered in 1979, and it has approximately 1% of total geological reserves, which is close to 300 million barrels of recoverable reserves. So it's a massive oil and gas reservoir were formed in the Jurassic and Cretaceous deposit, and reservoirs mainly consist of sandstone deposit in deltaic, fluvial, and shallow marine environments. And because of this, so we have very good permeability. So key problems, what is, okay. So we know that, I will skip this slide, it's boring, so okay. Yeah, and we did literature review based mainly on 1 Petra, and we found in open source data that there is close to 30 projects all over the world, and we did literature review of these projects and found maximum and minimum implementation conditions over the world. We know that From confidential information, SNF said sometimes it said more than 100 projects over the world. So it means that only 30% are brave to open this data for scientific society. So, and we found that Kalamkas field here in the green circle. We see we have very good oil viscosity for implementation polymer flood. We know that polymer flood implemented at 1 centipoise, but it's not best option. We know that melting point is using very high viscous oil to displace, to recover additional oil, and we think we are in good candidate for in terms of viscosity. And temperature is another advantage because lowest temperatures was 12 centigrade, and we are at 40 centigrade. It means we have good conditions. And low depth, 700 meters multiplied by 3, about 2,000 feet. And the most important, we have very high permeability. 500 MD, it's only average. So somewhere is a 2 darcies, 1 darcy. It's low consolidated reservoir sandstone. So we have delta, we have fluvial depositional environment. And most challenging thing here is of salinity, very high salinity, 13% of TDS and 8,000 calcium and magnesium concentration, which is contributing for concern of stability of polymer. So all these things, we are not first guys who says Kalamkas field is the best option to polymer flood. And our brave scientists from Soviet Union time found that Kalamkas field should be recovered at secondary regime. It should be polymer injected before water injection. No water injection, only polymer. That's why first pilots and full field implementation started since 1981, and production began in 1979. So just after, during the greenfield implementation. So totally they injected over the 52 injector wells, and we used hydrolyzed polyacrylamide manufactured in Japan, and we injected 10,000 tons or 8 million cubic meters of polymer solution with polymer concentration about 1,000 ppm, and achieved 1.16 million tons of additional oil recovery. If we multiply by 7, we get the barrels. 7 million barrels of additional oil. But we all know that Soviet Union failed at the late of 1980s, and main reason behind this was the low oil prices. So low oil prices, the country failure, all this contributed to stopping polymer flood implementation, such efficient polymer flood implementation, and switched to water injection and deteriorated oil recovery over the field. Then me and my colleagues come to consider again polymer flood injection, and although polymer flood not new technology, not novel technology for Kalamkas field, however, injection time is not same. So at the beginning it was no production of water, no injection of water, greenfield, recovery factor about 1–2%, and now we injected 25 years water, approximately 1 per volume already injected. Everywhere, high permeable sticks, water breaks through, high saturation near injectors, a lot of remaining oil which cannot be displaced by low viscosity water. So mobility ratio is here is about 7, or oil viscosity about 20. So endpoint relative permeability is 0.3. So that's why we have mobility ratio 7. So we started project here at the west part of the field in 2014, and we started another pilot at the east part of the field, which called East Pilot in 2015. Why we used 2 pilots? Because the operating company have 50% shares of CNPC, China National Petroleum Company, Zhongshio, and 50% of Kazmunagas National Company. So there is a competition between Chinese and local Kazakh peoples. And we should find the answer. So Chinese claim, it's very interesting story. So they said, Dachin oil field, we have very excellent experience. We started polymer flood at the beginning of 1990s. We injecting 11,000 injectors, and 1/3 of total production is contributing to polymer flood, right? And they said Kalamkas field is the best candidate for polymer flood. But they said existing well pattern is an inverted 9-spot where we have in center 1 injector and surrounding approximately 8 wells. If you use calculation, it's 3, 1, 2, 3. So, and they said we should infill first. We should to modify 9-spot to 5-spot, then start injection to decrease well spacing. Well spacing is 400 meters. They said well spacing should be 200 meters to improve, to stimulate the production. They said, okay, so do it. East pilot, west pilot, parallelly started. So here was a polymer from Western Europe, manufacturer, I couldn't say which company is it, and sorry. And east one is one company from Shengli oil field. Maybe you know them. They're also very famous. So this is the results of west pilot. So we started after 1 pore volume water injected, we reached high water cut 90% and recovery factor just over 20-something%, and we just see sharp decrease in water cut and increased oil rate. Oil rate doubled, and we did basic on hard data from using reservoir engineering approaches. We estimated our mobility ratio. It's oil cut versus depletion of recoverable reserves, which is developed by a very famous Soviet scientist called Lysenko. And we see that mobility, so here's mobility ratio 1, 2, 3, and over. So when mobility ratio increase, oil cut will decrease very sharply. So we found that oil mobility ratio before polymer flood was about 7, and it's consistent with our core flooding results with the rel perm identification. And after polymer flood, we see that mobility ratio is decreasing and tend to go to unit mobility ratio. So it's showing very clear that this result is good. And utility factor of west pilot here is close to 100 additional oil recovered per injected 1 ton of polymer. So we are Soviet Union countries, so we used to use SI units, so sorry if we cannot use field units. And East pilot also has efficient, but they not much effective as a west pilot. That's why they close it later. So during the implementation, we tested different type of sources. So we use it at beginning, production water, but we failed. So it should be compared, it should be considered rock and fluid compatibility. For example, we know Mangala field injecting seawater, and there is a lot of scaling, which is contributing to mechanical degradation. So we should think very well about water compatibility, water quality, because it's a how to say, is the most crucial parameter of success. If you fail with finding the water, your project will be failed. Then cost efficiency, will it be cheap or expensive? High production capacity, low TDS, high chemical stability. And also oxygen should be 0. So we have 2 different type of water source, and we found this is a production brine, 13%, and it's a Cretaceous water reservoir which have very similar ion composition but lower TDS, and the most important thing is dissolved oxygen. As Professor Searide mentioned, Stefan found that 46 ppb is a, how to say, kickoff point of oxygen. So we should be lower than 46, and we see that in production brine, we are not protecting our produced brine out of oxygen, so there is a lot of oxygen. So Cretaceous formation doesn't have any any oxygen, it has lower TDS, it hasn't oil, anything. That's why it's the best, and it's have a lot of capacity of production. So we choose it Cretaceous water. So these pictures from the field, we're measuring oxygen and so on. So we developed it from the beginning like a child. We started to, moving over the surface, and we raise it when we started to move, then run. So it's like this kind of concept. So we, over the 10 years, we developed the systematic laboratory studies to find best polymer which can be used. So it includes QA/QC, polymer rheology, core flooding, polymer retention test, displacement efficiency, and all in this kind of methodology. And this one is a already published paper in SPE journal in 2022, a paper called Field Demonstration of the Impact of Fractures on Hydrolyzed Polyacrylamide Injectivity, Propagation, and Degradation. So we have concern that polymer degrading. Why I came to this conclusion at the beginning, before enrolling PhD program, I found that polymer wellhead pressure not increase. I said, why? If Darcy law is right, very famous Darcy Henry, who lived in Dijon in France in mid of 19th century, if he's right, wellhead pressure should increase, and it should be correlated with the viscosity. If we inject in 20 centipoise, so it means wellhead pressure or well pressure difference between reservoir pressure and bottom hole pressure should increase 20 times. We have 50 bars of injection pressure during water injection. And during polymer flood, nothing changed. On top of that, we increased injection rate, and wellhead pressure doesn't increase. And I have a question, why? I asked the guys who implemented it, I don't care. I just inject, I take my money, I don't care. Go out, Marat, don't fuck my brain, just, sorry. And I started to investigate this. And we did core flood experiments, and we found we have vertical wells, and we found that this is a flux versus effluent viscosity injected. So 100% it means 20 centipoise, and 0 it means 1 centipoise. So if we assume that we have perforations, which is true in the Kalamkas field, we should have about 100 feet per day, and our polymer should degrade at least 70%. And if it's open hole, it will be a little bit better, but still we have 50% decrease. And if it fractured well or flowing deep in the reservoir, which is similar to core flood at low velocities, so polymer mechanical degradation is not already concerned. So, okay, we said, okay, this is not good results. 2018, I said, no, we should stop polymer flood. So there is a Marat before and after. Before, I claiming the polymer flood, not feasible. It's blaming, it's not truth. They just making money. I said, no, polymer flood cannot be feasible. So we go to the literature and we found the same correlation. So field assessment says that there is a degradation. Chinese, French company, Courtenay in France, Henan, Shengli, Daqing, Tambarejo, as the early tests. Madzen in Austria, Dalia, Bohai, everybody says that there should field assessment, direct measurement says that there is degradation, and it's correlated with our wells, with our core flood experiments. So if we are in right mind, why we lose our money? They say we are degrading polymer and they investing. It's not logical, right? So, and how we can get this very perfect response of water cut, increasing of water, oil production, decreasing of water production, increasing of oil production, like Milne Point today, we see very excellent results. It shouldn't be true, or it's failed. So, Nadyusha, Zobi in China, I don't know. It's cheating. Should be cheating or something else. So I said, okay, we should investigate it, and to do it, we need to do our field assessment to prove it. We have two proofs. We need a third one to be confident to stop the polymer flood or continue it. So we go to field, and I started my work career in the column cast field as operator, and I found during the operation, closing and opening the valves, I found if we stop injector, it would start backflowing. And this idea, coupled with the necessary to investigate mechanical degradation, become one hypothesis. And we start to develop this technology of assessment in field assessment of mechanical degradation. So it's very simple. It's a picture from the field. We connect mobile pump unit to the top valve through the special adapter, which is our novel equipment, and connect the sampler, and it should be some special valve which is not degrading the polymer. And after stopping injection of polymer, during repairment of the facilities is a very robust process, and we stop injection, open close this pipe valve, open master valve, top valve, and start to backflow. So we tested 8 wells out of 13 of injectors, so half of them. And all of them says no degradation, nothing. So why? So can you see the west pilot, east pilot, the wells with numbers, this red triangle is the polymer injectors, and labeled numbers is a wells which has been tested. And we can see it's representative, right? Is it representative to say, do we have degradation or not? So we found it no degradation, and we asked it, okay, we have two proofs. Should be mechanical degradation, but the third research said no degradation. Two opposite results. So we go further and did well test. We built whole plot, which is a cumulative injection volume versus cumulative injection pressure, which shows after water flood we have change in slope, which means our injectivity improved. Okay, I'll be fast. And we did step rate test, which shows that injectivity of polymer injection over water injector is 4 or 5 times higher. And finally, PTA analysis shows it's the fractures. So polymer inducing the fracture, and at the beginning, we saw that we're deteriorating our process, but finally we found that we're good. So no mechanical degradation. So it was an achievement. Also, we did some oxygen measurements. We found that if we inject high concentration of oxygen, which is 10 times higher than the requirement, and we have terrible degradation, even if we're not working good at the surface, formation, the reservoir will help you, because iron-containing mineral formation will quickly consume injected oxygen, thereby providing further chemical degradation. So we found two answers for two concerns. No mechanical degradation because of fractures, no chemical degradation in formation because of iron-containing minerals. It was two achievements. And also in west pilot, east pilot, do you remember I said we stopped injection and turned to water? We injected 50% of pore volume. We see very clear oil cut response, water cut decrease. And after changing to water, we have lost all this efficient, everything. So polymer breakthrough. We have polymer breakthrough, and it was very clear indication for us. We should inject polymer as much as possible when net present value is positive. And during implementation, we developed also as a polymer laboratory studies, polymer flood surveillance programs, well surveys, polymer QA/QC, pilot wells, monitoring, performance evaluation, etc. And we use it in East pilot. Chinese guys should be familiar with this equipment. It's a adductor type unit, which is common for Daqing oil field and Shengli oil field. And it's not protecting the system from the oxygen. We have terrible degradation, 45% in viscosity and 25% of concentration. And we're using PSU in the west part and no degradation. So we found that it should be PSU used to protect to be feasible polymer flood. And if you can see the picture from the field, is a ductor, big tanks, is a big construction, and PSU is mobile unit. It's very convenient to use. So we choose to use PSU for full field implementation. So all above mentioned is like a big concept. It's a systematic approach of implementation of polymer flood in the column cast field, which includes everything which I mentioned above. And we go to sweet spot selection. We developed an analytical equation based on simulation studies, which have depletion intensity, height of oil reservoir, layer permeability, net to gross, permeability, productivity index variation, and water cut. So instead of simulating half year one area, we can use this equation to calculate 1 second. And we found which one is the best, which one have feasible, and found which areas is feasible. So finally, based on this sweet spot selection criteria and concept, we've filtered 26 areas, including 80 injectors, which is 15% of total injectors. And we're planning to use PSU 100, 300, and 600, and we use one PSU for multiple horizons with different concentration, with different viscosities. So, and finally, here is a polymer consumption, so it will be interested for service companies. And we have a sensitivity analysis which shows the most contributing for feasibility is the OPEX. So if we decrease the price of polymer, we can expand 80 injectors to 120, 150. If it will be cheap or zero price, we will implement everywhere. So, conclusions. So, also we did calculations on, we know that carbon footprint, this Paris Agreement, Abu Dhabi CAP something 28 or something, it's very modern, and we should consider environmental impact. So we can save 60 million barrels of unwatered water production, and CO2 emissions should reduce at 27%. So thank you for your attention. It will be a pleasure to present this paper.
I think that I'm going to go right here because you have a question. We have time for a fast question.
That's it. Yeah, just fast question. So is fracturing when desired, do you think?
Huh?
Fracturing when?
Yeah.
Is that a plan?
No, it's not planned. It's just happened, and it's happened everywhere. Everywhere in vertical walls, everywhere. If someone says, I'm injecting polymer in vertical walls in matrix regime, you say, you don't know about your polymer flood, anything. Sorry for this true story. And I have QR code of my contacts. I know that I took a lot of time and no for QA session time. So just scan it and text to me via email, WhatsApp, anything, and ask the questions. Thank you.
Okay, that's great. And that is for question 7. So we are done. Thank you all very much for coming.